So welcome back. As always, the hardest slot to give a talk is right after lunch. But for this reason, we chose a very interesting and entertaining talk. So Lennert will give you an introduction to hardware hacking.
Thanks for the introduction. So my name is Lennert. The talk is about hardware hacking, and I'm going to try and show you some of the tools and techniques that a hardware hacker can try and use to compromise an embedded device. Now, on the first floor of this building, we have our hardware security lab. These are some pictures from the lab. So the top picture is an overview of 1/3 of the lab, I would say. Inside of this lab, we have all sorts of tools to try and attack devices. The bottom left picture is a laser setup, so you can shoot a laser at a chip to have it misbehave and in that way try and compromise the device. The middle is a side channel setup using a micro EM probe. And on the right, we have an FPGA board that is used by other researchers to try and implement a cipher secure against side channel attacks. So of course, the lab is not only about attacking devices, but also trying to implement defenses. Now, as an outline for the talk, we'll start with a quick introduction. Then I'm going to talk about the device lifecycle in the context of threat modeling. At first, my idea was to show you a few slides related to threat modeling specifically, but I think a few other speakers have already touched upon the subject, so I'm going to talk about the lifecycle specifically. Then we're going to look at the different types of embedded attackers and what they are capable of. And finally, hopefully we'll have some time left to talk about a case study related to Starlink. Now, if we talk about embedded devices, there's a big ecosystem behind them. This is just a few examples of all of the embedded devices that we have out there today. And of course, we're starting to connect all of these devices to maybe some smartphone apps that communicate with these devices. And of course, also a cloud system. Now, I see there's already a few people smiling in the audience. Yes, this is a smart sex toy that talks to an app and can be controlled remotely by other people. Obviously, this device wasn't designed with security in mind, and the slides are full with links that you can click on and then start reading more. So there's an entire story about this specifically. Like, what else are we connecting to the internet these days? Smart defibrillators. I'm not sure that's a great idea, but even payment terminals are, of course, being connected to the internet. Now, one thing I'm not going to cover in this talk is this backend or cloud infrastructure, because I only have 1 hour for this talk. But that doesn't mean it's not important, because you can, of course, imagine that if someone can compromise the entire cloud backend, that they can probably also attack all of the devices. One recent example that I thought was really well written, and I can recommend you all read, was by Sam Curry. And one day, Sam noticed that his modem provided by his internet service provider had been compromised. He noticed this because he noticed that some of the requests he was doing were being replayed by the modem a second time. This stood out to Sam. Sam himself is a researcher, and of course he wondered, how did this happen? Like, how was this possible, and how did the attacker achieve this? And what Sam figured out during his research is he figured out a way that he could update the settings of all of the modems from this ISP. And this entire blog post sort of walks you through all of the steps that Sam took and is really well written and well explained. Now let's start talking about the device security lifecycle. So when you do threat modeling for a device, it's important to keep in mind that the device will be deployed and has to be maintained as well. So under the lifecycle, we consider the design of the device, manufacturing the device, deploying it, maintaining it, and then hopefully also disposing of the device at some point. Now, of course, during design, if during design security is not taken into account, then we will not end up with a secure device. That's rather obvious. And in the end, we will come up with some requirements for a device, some security features that we require, for example, secure boot. And then in the end, you will buy a device from a manufacturer, let's say Texas Instruments or NXP, and you buy a chip with a secure boot feature. Now, of course, as a device manufacturer, you will most of the time blindly rely on these manufacturers to implement all of that securely. And that, of course, doesn't always happen in practice. Then once the device has been designed, it has to be manufactured, and typically manufacturing is outsourced. Then the question is, of course, can you verify that the product you get back from the manufacturer is really what you asked them to build? Now, there could, of course, be some intentional modifications done to the device or some unintentional ones. For example, you order a device with a specific microcontroller. It turns out this microcontroller is out of stock, so the manufacturer helpfully replaces this microcontroller with a different drop-in replacement, as they're called. Now, these drop-in replacements could have different vulnerabilities than the original chip you requested and can thus result in a compromise of your device. Then we have to deploy this device. We have to get it from the manufacturing plant to a consumer. This means that the device could be maybe intercepted and modified. I think we all know this famous example. And then, of course, once the device has been deployed, we need to probably provision it. We need to generate some keys, store those keys securely. The device might have to contact the backend. And then the question is, of course, can the backend verify that this device is legitimate and that it's not a fake device that someone made? And then, of course, the question is, what happens if I buy a device from Amazon, I open it up, I slightly modify it, and then realize that I don't really like this device after all? I send it back to Amazon, and then what happens? Will Amazon just resell the device and give it to a different consumer with my backdoor left in the device? These are all of the things we have to think of. Now, once all of these devices are deployed, we have to maintain them. They're going to be out there for a long time. The cloud infrastructure has to be maintained and updated. There have to be secure software updates for the device. A few days ago, there was a bug rediscovered in OpenSSH. You can imagine a lot of embedded devices are affected by this bug and, of course, have to be updated. Of course, there's also other threats. I think Bart also mentioned insider threats that can happen. This was a story from a few years ago where a Tesla factory employee was offered $1 million to insert a USB thumb drive into a server on the manufacturing plant. In this case, the employee didn't do this, but of course, there's no guarantees that other employees wouldn't have taken the $1 million. Another thing we have to think of, and maybe this is a good picture to see who the real hardware security nerds in the audience are. Does someone recognize the person in this slide? Okay, I'm the only nerd in this audience. That's good to know. This is Christopher Tarnowski, and Christopher Tarnowski was involved in the pay TV days. So there was a big sort of industry competition between different suppliers of pay TV, where one supplier started hacking the cards made by other suppliers, and then they all started accusing each other. This was an entire story, and you can read up, and there's even a documentary about this story linked here in the slides. Now, of course, maybe after 20 years, we want to dispose of this device, and you have to do it securely. Maybe we have to revoke keys, we have to erase data from the device, and so on. And then, of course, the question is, where does the device end up when it gets disposed? Well, I can tell you it ends up on eBay. And eBay is the nicest place to get all of your interesting and fun research projects, because you can even buy these days a used, of course, Stingray device that was at some point used by law enforcement. You can find Tesla infotainment systems on there that apparently still contain sensitive or personal information from the previous user. And you can even find your own baseband units from Ericsson on there. Now, if you look very closely towards the slide, I can even tell from which telecom operator this baseband was. And the question is, if this baseband is currently sitting on the carpet in someone's living room, do you think it was erased securely, or do you think I can still pull data from it? Now, one thing to keep in mind if we're talking about hardware security and embedded devices is that these devices are naturally always exposed to a hostile environment where there's constantly adversaries that have physical access to the device. And in some cases, the attacker is the legitimate owner of the device. And that, of course, makes it more difficult to protect against this attacker. Most famous examples come from the gaming industry, where gaming consoles have been physically attacked for many years, and that makes them some of the more secure devices out there today. Just to give you an example of how far some people might go to attack a gaming console and play games for free, this is an example from one of the Xbox gaming consoles. So here the idea was that this chip is responsible for verifying if a disk is legitimate or not. And inside of these chips, there's actually two dies stacked on top of each other and connected with bonding wires. And some people figured out if they disconnect one of these bonding wires, they can overwrite the firmware on this small chip and then essentially skip the verification of a game disk. So what would people do at home? They would count pins on this chip to get a precise location. They would take a small drill bit, make a very fine hole in this chip, break the bonding wire, reflash the firmware, and then play pirated games. So this is the sort of people you're up against if you're designing embedded devices. Now, of course, as consumers, threat modeling is much more difficult. Most people are inherently quite good at threat modeling. I think most of the people in the audience have figured out that wearing a seatbelt is a very good idea. That's some good threat modeling. But if you buy a device, it's much more difficult. There's no way that you can actually verify that the device you received is legitimate, that it hasn't been tampered with, and so on. And there's even stories where this happened in the past. So Ledger is a manufacturer of hardware cryptocurrency wallets. At some point, some of their data was breached and leaked. So a lot of customer data was leaked. Some people figured out they can actually now send letters to people that previously bought Ledger wallets. And with that letter, conveniently include a backdoored hardware wallet. So the letter would be an apology letter coming from the CEO saying, we're very sorry for losing your data, but here's a free cryptocurrency wallet you can use. Of course, if you used the cryptocurrency wallet, they would steal your coins. Another project is called Precursor by Bunny, where he tries to solve this project by making a device that you can actually verify. So you buy the device, you open it up when you get it, and you follow a series of steps to try and get some certainty that the device hasn't been tampered with. But of course, doing this for every device is not very practical. Now let's take a look at what an embedded attacker can do. We'll start by doing some basic exploration of a device and using some very basic techniques that I think everyone can do at home to try and analyze a device. And then we'll look at some more hardened devices and what other capabilities an embedded attacker has. Now, if you would go back home, you would go to the attic, you would try to find the device you're no longer using and open it up. It will almost certainly look like something like this on the inside. This is, of course, assuming it's an embedded Linux device. So we always have a central processing chip, a system on chip that contains the processing unit of the device. There's always some volatile memory, typically DRAM, and you can see this on a board because there's these squiggly lines or traces on the board that connect the two. On the other side, we have non-volatile memory. This is the place where all of the data is stored at rest, so maybe the firmware or the operating system of the device. And this is always interesting to analyze for software vulnerabilities. The system on chip typically has some debug interfaces, maybe UART or a JTAG or other interfaces. And these are always interesting to look at. In this talk, we'll look at UART because it's very common. And then, of course, like I mentioned, we want to read the contents from this non-volatile memory. Let's put this in practice. Here's a picture I took from a board. I think we can all quickly spot that this rock chip is the main system on chip on this board. It's a quad-core CPU. I told you there's these squiggly lines or length-matched traces on the board, and these are connected to the volatile memory. And finally, the non-volatile memory chip is this 8 gigabit eMMC chip. An eMMC is an embedded multimedia card. It's very similar to a regular SD card, but in a different type of package. Now, what else is on this board? There's a Wi-Fi module, there's a small microcontroller, there's an interface for a webcam, a Wi-Fi antenna, a microphone, and a speaker. Does anyone want to take a guess as to which device this picture came from? This is what a modern vacuum cleaner looks like on the inside. Because of course it needs a webcam, a microphone, and a speaker. Now the first thing we'll try and do is find some exposed interfaces to maybe get an easy way into the device. And one of the most common ones is UART, so that's the one I'll focus on, but there's many more. Most of the time it helps if you understand what these interfaces do, but there's also a lot of tools out there that you can just use to interface with these interfaces. One tool I pictured here is a TieGuard. It's a cheap multi-tool that can do UART, SWD, JTAG, SPI, and I2C, even at different voltage levels. So what we'll do is we'll look at the board, we'll try to identify where some of these signals might be exposed, solder some wires to them, or put some of these needle probes on the board, then connect the logic analyzer and see if there's any interesting data coming over these pins. So again, if we do this in practice, here's a few pictures of what this might look like on real boards. So to remember UART, we always need a ground pin, a receive pin, and a transmit pin. On some boards, you might see these labeled. That makes it easy for us. On other boards, they're not labeled, but you will typically see a header with 3 or 4 pins, and you can make an educated guess. This is likely UART. You solder some wires to it, you connect it to the logic analyzer, you reboot the device, and if there's any data coming out, then you know that you found the right spot. Let's do this on a real device. This is a DAB tuner. This is a component that you would typically find in a car, and this component is responsible for receiving DAB or radio signals. So I opened up the device, I saw that there were this debug header, I soldered wires to it, I connected the logic analyzer, I rebooted the tuner, and I saw some serial output. Then when I connected the USB to serial adapter, I received this output. I got a login prompt. I entered the very secure username root and super secure password root and logged in. And now you have a root shell on this device and you can start exploring. So you can imagine if you want to find an over-the-air attack over DAB into this tuner, then having this initial root access makes everything a lot easier. Now, why is this tuner specifically interesting? Well, as I said, it's used in cars, and specifically this one is used by Tesla. And Tesla says if you can compromise this tuner over the air and then pivot to the infotainment system, they will pay you $250,000 and they will give you the car to go with it. So if someone uses the information in this slide to get $250,000, then maybe buy me a beer or something. Another thing we'll often see is if you open up a device, there will be a lot of components that haven't been placed on the board, that were maybe previously populated for developers, but not meant for manufacturers. So there have been many instances where I would open a device and would find an unpopulated USB connector on the inside of the device, something you would never be able to reach. This is an example here of such a USB connector that's missing. Of course, we can put it back, connect to this port, and see if there's anything interesting there. The picture on the right are some push buttons that weren't populated. So these, of course, you can also put back and see what the function is of these. You have to remember that typically these unpopulated components are used by developers, and that makes them interesting for us as attackers. Another thing a lot of system-on-chips have are so-called strapping pins. And these are specific GPIO pins. When you pull them high or low during boot, they will force the SoC to do something else. So there's maybe a pin that you can pull high, and then the device will boot from USB instead of the normal non-volatile memory. This can be interesting for us as an attacker. But even a more interesting one is this one. And if you read it, it says, if this pin is pulled low, then maybe we will not authenticate everything, and otherwise we will. And of course, if you read this as an attacker, this is very interesting. A lot of manufacturers try to hide these data sheets from people, also because of common criteria, like Bart mentioned. This doesn't work in practice. A lot of them you can find on Google with some of these Google Docs, or you can try to buy the component from Taobao and then ask the Chinese supplier if maybe they also have a data sheet to go with the chip. So oftentimes you can always find a way to get to the data sheet. Now we've looked at these interfaces. Now we're going to try and get the software out of the device. So we're going to try and read the non-volatile memory. As I've mentioned before, these days we find a lot of these eMMC chips. Sometimes you can read them in circuit if the correct signals are exposed, and then you can even, in this case, connect them to an SD card reader and read the contents. For other types of chips, you have these convenient clips that you can clip onto the chip and then connect everything you need. In other cases, this doesn't work, and then you will have to remove the chip from the board. There's all sorts of tools for this. So most of the time, you can just get away with a cheap hot air or infrared rework station. And then on the other side of the spectrum, if we're talking more about forensic applications, then people might try to flip the board over and mill away the board, essentially, to reveal the chip. This is to not have too much heat stress on the chip itself. But this is very extreme, and typically you wouldn't have to do this. So if we take a chip off a board, so an eMMC chip as an example, these days this is very common, so they will look like this. These are BGA chips or ball grid array, so there's very small contacts on the chip. To give you some reference, this chip is 13 millimeters by 11 millimeters, so fairly small. For most of those, you have sockets, so you can just put the chip in the socket, connect it to a reader, and then dump it. Very easy to do. If you don't have a socket, you can even flip over the chip and just solder wires to the small contacts. This is an example of a smartwatch where the eMMC chip was actually stacked on top of the CPU. You can also see it here schematically. I removed the chip, I flipped it over, I connected wires, and was then able to read the contents from this. Typically, when you remove a chip, you also need a reader to then actually extract the contents. There's many readers out there. There's cheaper models that are very popular up to all the way like very expensive models. So let's say $100 and maybe $3,000. So there's a wide range of tools you can acquire. Now, if you go back home, you go to the attic, you find a device you want to look into, then you can also use an open source tool called FlashROM with maybe a Raspberry Pi that you already have at home and then try to read some non-volatile memory that way. Now, in this case, we've looked at UART interfaces. We've tried extracting non-volatile memory. Now, once you've extracted non-volatile memory, it becomes a software problem, right? Because then you're looking for software vulnerabilities. This is a hardware talk, so I'm going to assume that we didn't find any software vulnerabilities. So then the question becomes, what if the device has been hardened? What if the UART interface has been disabled? The JTAG interface has been disabled? We weren't able to find any software vulnerabilities. Then what can an attacker still do? So then the attacker will move on to physical attacks. This is the classical model of physical attacks. And when I say classical, I mean that it no longer always applies in practice, but it's still very commonly used, so I'll explain it anyway. So we'll divide up physical attacks into invasiveness and then how active or passive they are. A passive attack is an attack where we don't meddle with the device, we only observe what the device is doing. So these are typically called side channel attacks. Then when something is invasive, it means that we remove the packaging of the chip and we make physical contact with the chip. If it's non-invasive, we don't open the chip. Semi-invasive means opening the chip but not making contact. Now, there's a lot of different ways of packaging chips, and that's why I mean that this no longer really applies, because there's a lot of chips where you don't have to remove the package and you can still do the so-called semi-invasive attacks. Give you some examples. A power side channel attack is non-invasive and passive. It is passive in that we just observe what the device is doing, and it is non-invasive because we can measure the power consumption of a chip outside of the chip. On the other end of the spectrum, maybe we have a passive invasive attack. So it's invasive in the sense that we open the package and we will put needles onto the chip, but from that point onwards, we just observe what the chip is doing. So that's a microprobing attack, and then we consider it passive yet invasive. So let's talk about side channel attacks. I know a few other talks have already mentioned this. So here the idea is that we will observe something about the device. There's many side channels. I'll show some in the next slide. We'll often take multiple recordings while the device is doing normal operations. For example, the device is performing the AES cipher. We will record multiple of these observations and then do some statistical analysis later on to get the key out of the device. I think this is the most well-known example of how to explain to someone what is a side channel. I think we all know from the movies that we have these bank robbers that put their ear against the safe, manipulate the safe and open the door. Here, sound is a side channel, so the attacker is observing what is happening on the inside of the device and then adjusting the attack based on that information. There's a few other examples. I think Jonas will happily explain you the second one over the coffee break. Talking about side channels, there's lots of different ways of measuring side channels from chips. Power consumption is the most well-known one, but there's also EM emanations when a chip is operating. There is timing information, so if a certain implementation is not constant time, then based on timing differences, we can deduce information from a chip. A chip emits photons when it's switching. You can record these photons and again do side channel attacks. I have a few pictures of tools that you can use for these. So if you want to Google them at home and find more information, you can. And we move on to the active attacks, fault injection. Here we're going to intentionally meddle with the chip. We're going to have it do something it's not intended to do. And this typically violates the classical models you might have of a processor. So typically, if you write software, then you assume that the processor will execute exactly the software as you wrote it. If you write an if statement in the code, you assume the processor executes this if. With fault injection, we will make it skip this if or make it execute other instructions, essentially. Again, many ways of injecting faults into a chip. One of the earlier examples is again from the pay TV times, where in this battle between pirates and manufacturers, one manufacturer figured out how to detect fake cards, pushed the software updates to these cards that got them stuck in an infinite loop, and then people built what was called an unlooper, which would voltage glitch the card to skip past this infinite loop. So this was, again, stuff that people were doing at home back then. So injecting faults into chips, again, many ways to do this. We can meddle with the supply voltage of the chip. We can meddle with the clock of the chip. We can inject EM pulses into a chip. So instead of observing EM emanations, we now inject EM pulses into the chip. We can shoot lasers at chips. We can do body bias injection, and so on. So there's many tools that we can use to do this. Another more passive thing we can do is different imaging techniques. So the top picture is an X-ray taken from a single package. And if you look, not sure if it's visible, I think it is. So if you look inside of this package, you can see that there's two separate chips or dies inside of this package that are interconnected with bond wires. Now, if we know that there's information or sensitive information going over these bond wires, then it would be possible to sniff that data. A step further would be optical microscopy. You can do this both from the top side of a chip as well as from the back side. This is a picture taken from the back side of a chip. This is an infrared image. Then you can always get a bigger microscope. You can always get a SEM, or you can get X-rays that are the size of a facility, but that then give you nanometer resolution in 3D. So if you have something like that, that's of course the most fancy equipment you can get. What can you do with just imaging techniques? Well, some people extract ROM memories from chips just optically. So they will take a chip, depackage it, maybe even remove a layer of the chip, add chemicals to stain the chip, and then visually you will be able to distinguish a 1 from a 0 in certain memory technologies. Another thing people have done in the past, this was a paper where people were trying to reverse engineer a cryptographic or a proprietary cipher. What they did was they took a chip, they imaged it, they removed the layer, they made another image, they removed the layer, took another image, and so on. And then they started printing all of these images, put them on the floor, and started manually sort of tracing what the chip was doing, and in that way reconstructed the functionality of this chip. And nowadays, there's even some companies that do this commercially. When we move on, we go to probing attacks. So this is again an invasive attack because we open up the package and we put needles inside of the chip. This, of course, already becomes more advanced. You need more expensive equipment and so on. But there's quite a few things that people have done with these techniques. So, for example, some linear code extraction techniques where you would put a needle on the data bus, run the program, observe this one bit of the data bus in time, move the needle, repeat the process until you can get the entire data memory out. You can also try and reconstruct fuses. So this is an example where someone had a chip with a fuse that was blown. They depackaged the chip, put a needle on both sides of the fuses, and then connected both of the needles outside of the chip, essentially reconstructing the fuse and re-enabling whatever feature this fuse blocked. And then the most extreme example I saw recently was a big scanning electron microscope with microprobes on the inside of it. And with this device, they were able to probe a single 60 nanometer transistor with 3 probes at the same time. So really testing one single transistor in a modern day chip. So you can always get a bigger microscope. Then we can try to start modifying the circuit. Maybe the circuit doesn't really do what we want it to do. For this, you can use a FIP. There's also even stations where you have a FIP and a SEM in one, so you can both take high-resolution images and deposit metals, for example, on the chip to try and edit the circuit. Of course, these are very expensive pieces of equipment. They're not easy to use. You need a skilled operator, and then typically if you have a chip of which you don't really know how it was implemented, it's very difficult to find exactly what edits you might want to do. So there's a talk by Krzysztof Tarnowski, you might remember from one of the earlier slides, where he explains how he used one of these FIPs to attack what was back then considered a secure smart card. So with that, I want to end this part of the talk, and then we'll move on to the case study. So I want you to remember that an embedded device is always exposed to physical attackers one way or another. These physical attackers can have a lot of time and capabilities to try and attack the device. And if you design a device, you have to take this into account and think of what might happen if someone gets into your device. Now, I hope I convinced someone to go to their attic at home, pick up a device, open it up, and look on the inside. And if you do this and you get stuck, then I recommend you read this book, The Hardware Hacking Handbook, by Jasper van Woudenberg and Colin O'Flynn, as it really explains a lot of these different techniques in more detail. Does anyone already have a question about this part of the talk? No? Okay, then we'll move on to the second part. So this was a case study titled Glitched on Earth by Humans, a black box security evaluation of the SpaceX Starlink user terminal. Is there anyone in the room that has never heard of Starlink before? No? Okay, good. So this slide might be unnecessary, but let's quickly go over it anyway. So how does Starlink work, or what is Starlink? Starlink is a way of getting satellite internet all across Earth. And specifically what SpaceX wants to do different is they want to get high-speed satellite internet with low latency. The way they achieve this is by having many, currently around 6,000, smaller satellites in lower Earth orbit, so they're much closer to Earth compared to classical satellite internet systems. These are currently flying over us at speeds around 27,000 kilometers an hour. So if you think about your classical satellite dish, tracking one of these satellites would be extremely difficult or impossible. And so to be able to communicate with these satellites, SpaceX made a user terminal. And this user terminal is in fact a phased array antenna that is capable of electronically tracking these satellites. So how does this work? You buy one of these user terminals, it sends your data up to the satellite. That satellite might relay that information to another satellite over a laser, and then will beam the data back down to Earth to a gateway station. These gateways are in multiple locations on Earth, and they essentially allow your terminal to the satellites to connect to the terrestrial internet. Now, for some reason, SpaceX didn't want to give me one of the satellites. Not sure why. So we had to buy one of these user terminals, because that's the only thing you as a consumer can get your hands on. And if you think about it, if someone wanted to try and attack Starlink, then maybe they want to compromise one of the satellites. But to be able to compromise one, you have to be able to talk to it. And talking to it requires one of these special phased array antennas. Building one of these is very difficult and expensive. You need a company like SpaceX to develop it. So it makes sense that an attacker would just buy one of these terminals and try and compromise it. Now, whenever I use these slides, I always have to update them, because SpaceX is really fast at iterating over different hardware versions. So even though they only started selling these terminals back in 2021, you can see that there have been probably over 20 different hardware revisions of this device by now. I think there is not any other device where you will find this many revisions in that short amount of time. So even if I wrote /1/3, that's 3 different revisions. I just was running out of space. So we started with a circular user terminal. That's the one that's here on the desk as well. It was relatively big. And we moved on to a rectangular user terminal, which was smaller. There's also a larger rectangular one for high performance, so for business use. Then there's transceivers. There's not a lot of information available about these transceivers, but these might, for example, be used for military applications. And then the latest member of the family, released last week, is the mini terminal. So this is a terminal that's only 30 centimeters by 26. So these are getting very small quickly. You can also see that I marked this one in red, and that's because this one received a special update that we'll talk about at the end of this talk. When I did this research, we had access to a Rev2 Proto 2 and a Rev2 Proto 4 terminal, and even these two terminals, they had differences. So the Proto 2 terminal still came with a Cut 3, so a third revision of the system on chip, whereas Proto 4 came with Cut 4, or the fourth revision of the custom system on chip. Now, what we're going to do is we're going to apply all of the techniques and ideas that I presented in the first part of this talk to this device and see how we can analyze it. So we start by opening it. So we remove a big piece of plastic from the back of this terminal, and then we see this. So there's still this big metal shield. There's not much we can see, but there's this small cutout. And in this cutout, we can see a connector for power over Ethernet, a connector for motors that can tilt the antenna essentially, and then finally a UART connector. I think we all remember the UART connector from the previous section of the presentation. But in this case, there wasn't anything interesting on this UART connector. Because of course, SpaceX has learned their lessons also through Tesla, so they know that they shouldn't be accepting any invalid input on this terminal. So what can you see if you boot the terminal completely? It will say this is not a development terminal. It will still give you a login prompt, but whatever password and username you enter here, you will never get in, because it's not a development terminal. So we had to go a layer deeper. We removed the metal backing from this PCB, and then essentially you get also this here on the desk. And I marked some of the more interesting areas here, but for us in this talk, the area with the system on chip is the most interesting. If we can compromise the system on chip, then we can control the entire terminal, and then we can start exploring the network infrastructure. So if we zoom into that part, then it looks somewhat like this. So we can again apply the same technique. We see immediately this is the system on chip. There's some of these squiggly lines going to DRAM chips. There's again an eMMC chip, so a type of SD card. There's also a secure element, and that's something I'll talk about more at the end of the talk. And then we have some of these pull up and pull down pins, or strapping pins, that in this case tell this system on chip which of these many different hardware revisions this specific terminal is. Now, the system on chip in this case is a custom quad-core ARM Cortex-A53 processor, so quad-core CPU, made by ST Microelectronics. ST doesn't sell anything publicly that is similar to this chip, so that means that we don't have any data sheets, and there's no easy way to get a development kit, for example. Another thing we can do is this system on chip has a metal shield on top. If you remove it, then you get the backside of the chip. From the backside of the chip, we can make an infrared image that looks like this. What can we tell from this picture? Well, if you've looked at some of these pictures before, you can actually tell that here and down in the corner, there are the 4 CPU cores. And for certain physical attacks, it's convenient if you know which parts of the chip are physically located where. Of course, the next step for us was to try and extract the non-volatile memory, the software from the dish. I did this with an SD card reader. I found some of the correct signals exposed here on test points. You can connect it to a computer and then just read it as you would read an SD card. This was sort of a makeshift solution, but you can actually buy some adapters online that make this easier to do. Now, on newer hardware revisions of the terminal, you could no longer do this. You could no longer read the eMMC chip in circuit because they had removed all of the relevant test points. So in that case, you do have to desolder this chip, put it in one of these readers, extract the firmware, reball the chip, so reform these small little solder balls, put it back on the board, and so on. This is all relatively easy, but very tedious if you have to do it multiple times. So another solution you can do is you can make something called an interposer. You actually solder a small PCB to the board and a small PCB to the eMMC chip, and then you can actually remove and reattach the chip multiple times. And this interposer is something you can reuse on multiple devices. So here, for example, I have installed one of these in a Google Chromecast. If you're trying to find attacks related to secure boot where maybe you want to try and modify a certain partition, then this is very convenient because you can quickly iterate your tests. So now we extract the eMMC chip. We have this big binary dump that contains a lot of different partitions and that are interesting to analyze, but I didn't have time to look at all of these separately in this talk. There's a blog post online with more information about this. So what you should take away from this slide is that all of these partitions are either trusted firmware from ARM, they are signed FIT packages, they are DM Verity protected or Lux protected. So DM Verity protected are sort of signed partitions that you cannot modify. Lux partitions are both encrypted as well as integrity protected by Lux, and the keys for these Lux partitions are stored in eFuses. So what you should really remember is that if you would modify something on this eMMC and you would put it back, the dish would be able to detect it and would not boot. And of course, this means that we then have to move on to these more advanced physical attacks that I mentioned earlier. But now that we have the firmware, we might as well take a look at what's in there. There's quite a lot of interesting information in there. So there's even nicely documented shell scripts that explain you how the terminal will make sure it stays at the right temperature. You can see which frequencies are being used by the terminal to communicate with satellites. You can even see what type of lasers are used up in space. And the reason you can see this in the terminal firmware is because there's a bit of overlap between the firmware of the satellites and the firmware in the terminals. Another thing we found in this firmware that was interesting are development geofences. Something a lot of manufacturers struggle with is development hardware. If development hardware leaks, that's always interesting for attackers. For example, Microsoft had a big issue with this, with development gaming consoles ending up on eBay, people using those to cheat online, and so on. So what SpaceX does is, if the terminal starts up and it gets a GPS location, it will check if it's inside of one of these locations. Or if it's a development terminal, if it's outside of one of these locations, then it will trigger an alarm, and SpaceX will know that one of their development units has escaped and where it is physically located. Some of these locations make a lot of sense. This is a parking lot next to a SpaceX building. It makes sense that they would want development hardware there. This is the Connections Museum in Seattle, which for some reason is allowed to have development hardware. I'm not sure why. I also found a big villa in the middle of nowhere somewhere in the US that was allowed to have development hardware. But of course, disclosing that location was a bit too sensitive. Now, if someone really wants development hardware, if you zoom in far enough on Google Maps, you can actually see that there are some of these terminals on top of this parking lot. So all it takes is driving to LA, going up in this parking lot and taking one of the terminals with you. Now let's try to get a root shell on this terminal. And I showed you before that this terminal, when it's done booting, it prints development login enabled and then no. And if we look at the script that implements this, we can see that it prints development login enabled. Then we see that it does a check. So it's checking if this is production hardware or not. If it's not production hardware, then they will set a new password. And this hash is actually Falcon. So the password is Falcon. Now, of course, since we have a production unit, we cannot make this terminal believe it is development hardware, and we wouldn't be able to log in. Luckily, there's this thing called fault injection. So if we look at this on a more physical layer, we can see the first print statement. Then we can see that there is this 2 millisecond gap, and then the terminal prints no. So we know that somewhere in this 2.3 millisecond gap, the terminal is performing this if check. And so if we hit the terminal with a hammer at the right moment in time, then maybe we can skip this if check, have the terminal install this password, and then we can log in. There's multiple ways to inject faults, as I've already explained. And if we have a chip like this with the backside exposed, then we start thinking about very fancy fault injection techniques, like our laser, for example. But in this case, that wasn't practical, because this terminal is very big. Most electronic devices are not this big, so all of the equipment we have is not designed to hold something this big. So this is the box in which our laser is situated. This board would never fit in there. And then if you think about later on connecting the terminal back to the satellite, that would mean moving this laser setup up to the roof of our building, which is of course not very convenient. So instead, what we did was voltage fault injection, one of the most basic fault injection techniques. And the way that works is, or one of the ways you can do voltage fault injection is, if we look at this target processor, so the system on chip, this system on chip will have multiple voltage domains. So there will be a domain for the GPIO pins, there will be a domain for some other peripherals, maybe the DRAM runs at a different voltage and so on. But the voltage we're really interested in is the core voltage, so the voltage that supplies the CPU cores, because that's the component we're trying to attack. So once we've located this core voltage supply on the board, we can attach a MOSFET to this core voltage and essentially create a short circuit between the core voltage and ground. And if we do this for a certain amount of time, in the order of nanoseconds, so 100 nanoseconds, 200 nanoseconds, then we can have this chip perform faulty instructions. How does this look in practice? In this case, I started by using a chip whisperer Lite. This is a commercial tool you can buy. It's cheap and it's meant to teach people about this type of attack. So I connected it to the right location on the board, so I determined this is the core voltage supply. And then we essentially started trying different parameters. So how long do we short the supply to ground? And when in this 2.3 millisecond window do we short it to ground? If we try this often enough, then eventually you might get something like this. So you see the dish prints development login enabled. It even prints yes, but at the same time we've caused a null pointer dereference in the kernel, so the entire system still crashes. We try this a few more times, and eventually you really get lucky. It prints yes. We log in with the username root, we log in with the password Falcon, and we now have a root shell on the terminal, and then you can start exploring the network. Now, this was nice for us because this showed to ourselves that we can actually inject faults into the chip, which is a good first step. We also reported this to SpaceX, and they were able to also reproduce the issue on their end. But the issue with this attack is that it's very slow, because we can only do one attempt for every boot cycle of the dish, which takes 12 seconds. The attack is not very reliable, and that means that it can take many, many hours before we once get lucky. And of course, once we had reported this to SpaceX, it was very easy for them to just not have this check in there anymore at all, and then you were locked out again. So instead, if we can attack the very first bit of code in the chip, then we can iterate much more quickly over our faults that we inject, but also the first bit of code in a chip cannot be changed. It is baked into the chip when it is produced. So if you can attack that bit of ROM code, then there is no way for them to fix this in the field. And that means that we're going to try and attack the root of trust of the system on chip. A root of trust often looks something like this. We have the ROM bootloader, so the first piece of code that executes when a chip starts. This is considered immutable because it's in ROM inside of the chip. This is responsible for loading and verifying the second stage, and it's going to verify essentially a signature over this second stage using a root of trust public key that's burned into eFuses inside of the chip. So how does this work? The idea is that everything that's not within this single chip is considered untrusted. So if we load the second stage firmware from the eMMC, we're going to assume someone has tampered with it, and we want to try and detect it. I'm going to skip this part. So how does this actually work? So the ROM bootloader starts, it will load the certificate from the eMMC and will verify a signature that's contained within this certificate. If the signature of the certificate is valid, then it will actually load the second stage firmware, compute a hash over this, make sure that this is the same hash as the one that was contained in the certificate, and if all of this is valid, then execute the second stage firmware. Now, there's two obvious points in time where we can try and attack this with fault injection. So we can either try and attack the certificate validation, or we can try and attack the hash comparison in the second step. The setup for this looks relatively similar, but we made a few changes. I removed decoupling capacitors to make the system more unstable and more susceptible to glitches. And it turned out I really had to remove this to make this attack work. And secondly, we added one of these EM probes that I showed in the first part of this presentation. And this EM probe gives us some side channel information about what the chip is doing. So if you look at one of these side channel traces, so in blue we have the EM side channel, in black we have the UART data. And essentially, at this point in time, the terminal is telling us, we've loaded the certificate from the SD card, and we're going to start verifying the certificate. Then you can see that it's doing all of these calculations to verify the signature. Now, if at this point where the computation starts, we make a short on the power supply, then we get this. So you can see that the entire signature computation is essentially skipped. And what happens is the terminal says, I've loaded the certificate, I'm going to start verifying it, and it's immediately done verifying it. So it thinks this certificate is valid. And since we can do this, it means that we can modify the second stage firmware that's on the external eMMC. And that means that we can also disable all of the other signature checks that that stage would do, and so on. So from this point onwards, we have a complete compromise of the terminal, and we can execute whatever code we want, even from the very early boot stages. Now, there's a lot of things you can do at this point, too many things that I have time for in this talk. But one of the interesting things we found is that SpaceX had actually considered that someone would go through these lengths to try and attack their terminal, because inside of the ROM bootloader, there was actually code to try and detect and prevent this type of attack. The issue with the countermeasure in this case was that it was designed with a certain mental model of how a fault would affect the chip, and that mental model didn't really correspond to reality. Now, one of the issues I still faced was that I had removed these decoupling capacitors to destabilize the system, but by removing them, I made the system so unstable that during later boot stages, when the clock frequency of the chip is increased, the entire system would crash again. So I had to come up with a way to enable and disable these decoupling capacitors at will. This turned out to be quite frustrating, and I couldn't find anyone else that had done this before. So I started with some really manual soldering experiments. I tried a lot of different combinations of switching elements and the way they were connected and so on. But finally, the first solution that did work was this. So this was a custom PCB soldered on top of the existing one with 2 capacitor banks and then also 2 MOSFETs to switch on and off these capacitor banks. So this means we now have a full attack. We can compromise the ROM bootloader. We can switch on the decoupling capacitors. We can get a root shell in the Linux operating system and start exploring the network. But you can see from the previous slides, this is still a pretty cumbersome setup to move to a roof, because there's still an oscilloscope attached, there's still power supplies attached, signal generators attached. This is not very convenient. But either way, I decided I have the full attack working. I'm going to already report this to SpaceX. And they came back and they said, well, that's a very nice find. Maybe we can send you an SSH key, so you can just SSH into the terminal and continue from there. Now you can imagine that at this point I was way too far down the rabbit hole to accept a YubiKey. And so I decided to try and make a mod chip. So what we did was we tried replacing the oscilloscopes and all of the fancy equipment with cheap off-the-shelf components. So this is a Raspberry Pi Pico microcontroller. This board costs like $5 or $7. And we're going to attack the chip like this. This was the first setup that worked, but still quite messy. So we made a custom PCB. So I put this terminal under a flatbed scanner, made a high-resolution scan, and then in Inkscape, I traced the board layout. You can import this into KiCad and then design a PCB. So this is the final result. So you have the Raspberry Pi microcontroller slightly overclocked. I picked this microcontroller because it has a very nice feature called programmable I/O, sort of what some people might know like from FPGAs, but more convenient to implement. And this microcontroller is essentially driving this MOSFET driver that then drives the glitch MOSFET and the 2 decoupling capacitor MOSFETs. This design is open source on GitHub, so if you want to hack your own terminal, you can try and reproduce this. This is the mod chip installed on the terminal. It's the same terminal we have here, so if you want to see it up close, you can. Of course, still, putting this on a roof, not very convenient, because if something goes wrong, I have to go up to the roof. So I went to the mechanical workshop downstairs, and they made this very nice solution for us, so we can actually just hang the dish outside of the window and then use it like that. Of course, at this point, I thought it was game over, because I can compromise the ROM bootloader. I can execute whatever code I want. There is no way SpaceX can actually do anything about this in the field. Now, it turned out that when I did a firmware update, SpaceX actually still had one tiny e-fuse that they could blow that would stop the terminal from outputting anything over UART. And this was, of course, very frustrating for me because I was using the UART information to trigger my fault on. And of course, this means that we had to improvise, adapt, and overcome. Luckily, I had already been working on the terminal for a long time, so I had logic analyzer captures of while the dish was booting. I could take new captures when the dish was patched, let's say, and I had these nice side channel measurements. So I could simply retake these measurements, figure out what moment in time I had to inject the glitch again, and then trigger on one of the eMMC data lines that I could connect to from here. And then within a day, I could regain access to the terminal. Now, SpaceX really thought about the fact that someone would try and go through all of this effort to attack the terminal because they had a separate secure element on the board, as I mentioned earlier. And this secure element is a sort of like a SIM card, a very small but secure chip that in this case is the identity of the terminal and is responsible for doing mutual TLS with all of the backend services. So whenever the terminal connects to a backend, everything is mutual TLS and the client side is done by the secure element. This makes everything very tedious and annoying because all of your classical network testing tools don't work with this. They don't have support for this. So I implemented support for this chip in a TLS Lite NG, like a Python implementation of TLS to make things easy. And then I implemented a proof of concept where I could download all of the different firmware revisions of the terminal and analyze differences, essentially. So what's next? People can build this mod chip, like I said. So this is a picture that someone else built this mod chip and then tried attacking their own terminal. There's many things you can do. I think looking at the networking infrastructure is very interesting, but it's not really my expertise, so I leave that to the other researchers. So to conclude this part, what we've shown here is that we can bypass secure boot using voltage fault injection in the ROM bootloader. We did this on a quad-core Cortex A53 processor, without any documentation, without any open development samples. And we figured out a way to enable and disable decoupling capacitors dynamically. And then, of course, these fault injection countermeasures are very nice, but they're only as good as the model that was used to design them. And in this case, the model did not correspond to the reality. I would say that all in all, this is a very well-designed product from a security standpoint. It didn't have any obvious, or at least not obvious to me, low-hanging security issues. And in contrast to many other devices where once you gain a root shell, it's sort of game over for the entire system, that wasn't the case here. As I said, I reported all of these vulnerabilities. The team at SpaceX was very responsive, and they even released a statement about this research and sort of the threat model that they have in mind for this terminal. Now, I said that there's a new terminal released last week. This is the mini terminal. And this mini terminal has yet another silicon revision of the system on chip. And in this case, SpaceX decided to incorporate Crypto Manager Root of Trust IP by Rambus to try and prevent the types of attacks I've done. So this IP specifically tries to do secure boot in a secure manner. And of course, I don't really know how secure this actually is because these terminals have not reached Europe yet. So with that, I want to end this talk. And if there's any questions, I'd be happy to answer them.